Welcome viewers to today's presentation. My name is Blessing Bilson and I'm in the group 5 of the computer architecture group distribution. My group is presenting on bank memory, associative memory and the cache memory. I will be taking the bank memory, so let's get on with it. The bank memory, as the name stands, bank and memory. We all know what a bank is. A bank is like a storage place, and a memory is also a storage location. But in banks, we have different accounts, and these accounts represent different locations of storage. So just like the idea of bank and memory, the bank memory also suggests an idea of different memory locations. The bank memory, also known as a segmented memory or memory banking, is a memory management technique used in computer systems to overcome limitations in addressable memory space. This technique is often employed in microcontrollers, embedded systems, and older computer architecture where the available address space is smaller than the total amount of physical memory. So all what this is saying is that the bank memory is also known as a segmented memory or memory banking. And it's a memory management technique which is used to overcome limitation of memory space. This technique, according to our research, is an old technique, that is out of date. Let's move on. The basic idea behind bank memory is to divide the physical memory into multiple banks or segments, each with its own address range. The processor can access one bank at a time, and by switching between different banks, it can effectively access more memory than its native address width would allow. This is telling us that with the idea of bank memory, the memory location is divided into different groups or multiple memory locations. These memory locations are also known as banks or segments. And with each bank or segment, it comes with its own address range. This allows the processor to access one address range at a time, which is one bank at a time. And by switching between different banks, the processor can effectively access more memory than having one whole memory space would allow it to. Memory division. The total physical memory is divided into several banks. Each bank has a distinct address range that the processor can use to access it. As I said earlier, the banking memory system or technique divides memory locations into different storage spaces, also known as bank. And this memory division tells us that each bank has a distinct location, and the location allows its distinct location or address allows the processor to access it. Let's move on. The bank selection. The processor uses a mechanism such as a control register or special instruction to switch between different memory banks. The selection process determines which bank address range is currently active and accessible. This is telling us that before the processor can access a memory location in a banked memory system, the processor uses a mechanism. And an example of that mechanism is a control register or a special instruction. And this allows it to switch between different memory locations or different memory banks. And this process of switching determines which bank is active and accessible. That means the bank which the processor is able to access at that moment is the active and accessible bank. Let's move to bank switching. When the processor needs to access data in a different bank, it performs bank switch. This involves changing the active bank so the processor can access desired memory range. This tells us that the searching of information by the processor in a bank memory system is not something simultaneous. That is, before the processor can move to a different bank location, it has to switch from the active bank to a different bank. And this process is called bank switching. The bank switching allows the processor to change between the banking system. That means the active bank. So the bank which is currently accessed by the processor can be changed to a different bank. And this is done by bank switching. That is that for the bank memory. My colleague will take it from here.
I'm Daniel Watson, and today I'm presenting on bank memory. And I'll start with the usage. Different part of the program or data can be stored in different memory banks. The program must manage bank switching appropriately in order to access the required data. Bank memory particularly uses systems with limited address space, as it allows systems to effectively utilize larger amount of physical memory without requiring a wider address bar, which could complicate the system's design. However, bank memory also introduces complexities in terms of programming and managing the memory access patterns. An example of a scenario where bank memory might be used in microcontrollers with 8-bit processors that need to access more than 256 bytes of memory by using bank memory. The microcontroller can access multiple banks of memory, each containing 256 bytes, even though the native address width is limited to 8-bit. While modern computer architectures have evolved to provide larger and more linear address space, bank memory remains an important historical concept that played a significant role in engaging memory usage in early computer systems, which means bank memory has been outdated. Now moving on to associative memory. Associative memory, also known as content addressable memory, the type of computer memory that enables rapid searching and retrieval of data based on its contents. Based on its content means when a query is given out, it uses a keyword based on a query to search for data. And the reason why it's even faster is because the query doesn't have to be completed in order for it to find the data. And okay, moving on. It's designed to quickly determine whether a given data item is stored in its memory. Retrieve its associated information if it exists. This makes associative memory well suitable for applications such as caching, database management, and hardware lookup tables. Now, NDN and my other colleague continue from the key characteristics of associative memory.
Hello, I am Agyemang-Prempeh, and where my colleague from he started associative memory, and I'm to continue with the key characteristics of associative memory. So, one example of associative memory is parallel search. One aspect of the associative memory is the parallel search. Unlike the traditional memory, which requires sequential searching based on memory addresses, associative memory enables parallel searching based on content also. This allows for search faster data retrieval. Like when searching data, this is not where you have to go and be searching for the location of the memory bank. Immediately you just type the content of the file you put at the particular memory. It gives you the required data that you are searching for. So let's go to the next one, which is the high-speed access. Associative memory is optimized for high-speed access, while high-speed data access and retrieval. It's particularly useful when the time it takes to search for data is critical. Instantly, high-speed access. Associative memory is optimized for high-speed data access and retrieval. Unlike the parallel one, it's not when you are going to type or go and look for where you save your data or something. But this is where you just type the content and then everything over there. Because it's well with high speed. Like the speed is very micro, but you know, very, very close. Retrieve your data and everything. So let's go to the usage. 6. Associative memory is commonly used in the CPU. And you all know the function of the CPU, which is the brain of the computer. It keeps data for short, to quickly catch up a specific memory block is present in the cache. This helps improve the speed of the memory access in modern processors. Next example, bit priority. Associative memory operates using bit level priority, which means it compares multiple bits of data in parallel to determine matches. So let's go to the next example, applications. Aside from caching, associative memory is also used in networking devices for writing table lookup. In database system for indexing and searching, and in hardware acceleration for tasks like pattern matching and image representation. So let's go to the last aspect of the characteristics. Hardware implementation. Associative memory can be implemented using specialized hardware, which can include arrays of cells that perform the content-based comparison. While associative memory offers advantages in terms of fast retrieval based on content, it also has some limitations, including increased complexity, high cost, and the tendency to consume more power to traditional memory systems. Overall, so in conclusion, this is how the associative memory works. Overall, associative memory is a specialized memory architecture that provides significant benefits in situations where rapid content-based data retrieval is crucial, especially in systems that require high-speed data processing and decision making. So this is basically what we talk about, associative memory and then the characteristics and how it works and disadvantages and advantages. The disadvantages is quite expensive because you are going to consume more, you need more money to implement such a memory into your computer for processing. So I'll end my presentation here for my colleague to continue with the cache memory. Thank you.
Hello, my name is Bredo Maxim Team, and I'm presenting on cache memory. You all may know cache memory is a high-speed memory that is used frequently in access data. It is located between but closer to the CPU. That's the main memory that allows fast access times. Most purpose of cache memory is reduced to average time it takes to access data from the main memory. It works by storing a copy of frequent access data in a smaller and faster memory so that the CPU can retrieve the data quickly when needed. And this helps improve the overall performance of the whole system. And the CPU in memory computers are extended faster and execute instructions at incredible speeds. However, accessing data from a main memory, which is the raw, is relatively slower compared to the CPU's processing speed. And This difference in speed is known as the memory hierarchy gap. In quotes, to bridge this gap, the cache memory is used. The cache memory operates on the principle of locality, which means the program tends to access data nearby in memory. There are two types of cache memory, which are the instruction cache and the data cache. The instruction cache stores the instructions of the CPU. It stores the instructions that the CPU can execute, yes. And the data cache stores data of the CPU, which will record. So for the cache memory, it is organized in multiple levels, which we have L1, L2, L3. But the L1 is the first level of cache, which is known as the L1 is the level cache, which is the smallest but the fastest, which is known as L1. And the second level cache is known as L2, which is larger than the L1, but is slower. And we have the L3. The L3, that's the third level cache that is mostly used in modern computers, but it's larger than L2, but it's slower than the L2. Yeah. So I'll end here, and my other colleague will continue for here.
My name is Agyemang-Prempeh. So I'm continuing from cache memory. But first, let me retouch on what my colleague just said. So cache memory is organized into a hierarchy with multiple levels of cache. The first level cache, also known as the L1 cache, is the smallest but fastest cache, and it is usually built directly into the CPU. The second level cache, also known as the L2 cache, is larger but slower than the L1 cache. Some systems may also have a third level cache or L3 cache, and if they do, it's mostly larger but slower than the L2 cache. So we continue. When the CPU needs to access data, it first checks the cache. If the data is found in the cache, it is called a cache hit. So we take note of the word cache hit. So we only call something cache hit when the data can be found in the cache before access. And if the data is not found in the cache, it is called a cache miss. So if you want to retrieve data quickly and you cannot find it in the cache, it's called a cache miss. And the CPU has to retrieve the data from the main memory, which takes more time. The cache memory is an important component of modern computer systems as it helps to improve performance by reducing the time it takes to access data. It is especially effective for programs that exhibit a high degree of spatial and temporal locality, meaning that they access data that is nearby in memory, which is kind of similar to the associative memory, and that they access the same data multiple times. So, the cache memory is a crucial component of modern computer systems that helps to improve performance in various computing scenarios, such as gaming, scientific simulations, and data-intensive applications. It helps reduce the latency of memory access, enhances instruction execution, and optimizes data flow within the system. As you can see here, it's a picture of how the cache memory looks in the computer system. So, in conclusion, I want to combine everything we've said so far. The bank memory kind of serves as a storage for the data, but it has been divided into segments. And then the associative memory helps in faster retrieval of data.